Hi, this is the next video in the functions chapter. So for the next few videos I'm going to look at something called modulus functions. Now you'll have seen the symbol for modulus before. We use vertical lines like that to represent a modulus. And you'll have seen that before in, for example, vectors, when we've talked about the magnitude of a vector. The modulus symbol really just means the absolute value, so the positive value. So modulus, or the absolute value of x, so it's just the size of the number rather than the sign of the number. For example, if I write modulus 4, well, modulus 4 equals 4. Modulus negative 4 also equals 4. So it's just the size of the number rather than the sign. Okay, so that's what the modulus modulus is. Now you are going to have to sketch and solve equations involving two different types of modulus function. Type 1 is something of that variety, where y is equal to the modulus of the whole function, or type 2, where y equals the function of the modulus of x. Now they look pretty similar, but they act in different ways. Okay, so in order to demonstrate how to sketch these, we're going to actually plot a few graphs, and then you'll be able to see what the properties are and then be able to sketch them. So the first two examples we're going to look at are of the form y equals modulus of the whole function. So in terms of algebra, you might write it like that, or you could use function notation and you might see it written like that. Okay, so that's what it'll look like in the question, and you'd be expected to sketch that rather than actually physically plot it. But just so you can understand what's going on with the coordinates, I'm going to plot it. So we'll start off where x equals 1. Where x equals 1, y equals the modulus of 1 plus 2. So the modulus of 3 is 3. When x equals 0, y equals the modulus of 0 plus 2. So the modulus of 2 is 2. Where x equals 1, minus 1 plus 2 is 1. The modulus of 1 is 1. When x equals minus 2 plus 2 is 0. The modulus of 0 is 0. When x equals 3, minus 3 plus 2 is minus 1. Now the modulus of minus 1 is 1. When x equals minus 4, minus 4 plus 2 is minus 2. The modulus of minus 2 is 2. So you can see that when I've substituted a negative value, well, a value for x in here that's made this be a negative, I've basically, for the y value, ignored the sign. Okay, so we plot this, 1, 3, 0, 2, minus 1, 1, minus 2, 0, minus 3, 1, minus 4, 2. So we end up with a graph that looks like that. Okay. Now the original graph of just y equals x plus 2 would have carried on down here. So what's actually happened is that you've got the original part of the graph, and then the bit that would have gone below the x-axis, if you look, you can see that that is actually reflected in the x-axis. So this is the initial part of the graph, y equals x plus 2. But then where it's gone below the x-axis is actually reflected in the x-axis. Now this bit here, the whole thing is the modulus of x plus 2. But in terms of each separate little stick, this bit, that's the graph of y equals x plus 2. The equation of this is actually the graph of y equals minus x plus 2, which is minus x minus 2. Because if you look, it's got a negative gradient, -1 gradient, and if I was to carry that on, that would go through minus 2 on the y-axis. Okay, so this bit is as if that's the positive version of that, and then this bit is the negative version of all of that. Okay, the whole thing together is the modulus graph. Let's look at the next one. So here we've got a quadratic. This is still of the form f of modulus of the whole thing. So again, if we work out some coordinates, for x is 3, 9 minus 6 is 3, modulus of 3 is 3. When x is 2, 4 minus 4 is 0, modulus of 0 is 0. When x is 1, 1 minus 2 is minus 1, the modulus of minus 1 is 1. When x is 0, 0 minus 0 is 0. When x is minus 1, 1 squared, minus 1 squared is 1, minus 2 is 3. When x is minus 2, 4 minus 4 is 8, modulus of 8 is 8. So if we plot these, 3, 3, 2, 0, 1, 1, 0, 0, minus 1, 3, and that one's gone off. So that graph, I'm not just going to make a W shape because it was supposed to be a quadratic. If that was to carry on, that would go down like that. Okay, so what's happened is that's the graph of x squared minus 2x. The graph of modulus x squared minus 2x is actually that. So that bit there that's gone below the x-axis is actually reflected in the x-axis. Okay, so that's what we should have. That's the modulus graph. These two bits are part of the existing curve, proper curve. So that's what those two bits are. This bit here, this bit is y equals negative x squared minus 2x. So negative x squared plus 2x. Okay, but the whole thing together is the modulus function. Okay, so notice on both the graphs, the modulus, there is no negative value of y. That's because this f of x is in effect the y coordinate, and if we're taking the modulus of all the y coordinates, then y is never going to be negative. Okay, so that's those two. So we can consider the normal graph, and then anything that goes below the x-axis then gets reflected in the x-axis. So let's just look at how that differs from this one. So this is f, y equals f modulus x. So that's written like that. If it was modulus f of x, it'd be the modulus of the whole thing. So those are different. Okay, so what this one means is that when you substitute in, you take the absolute value before you work out the y value. So when x equals 3, modulus of 3 is 3, 2 times 3 plus 1 is 7. When x is 2, the modulus of 2 is 2, 2 times 3 plus 1 is 5, 2 times the modulus of 1 plus 1, 2 times the modulus of 0 plus 1. Now this is where it's different. The modulus of minus 1 is 1. 2 times 1 plus 1 is 3. Modulus of minus 2 is 2. 2 times 2 plus 1 is 5. So it's slightly different. So you're substituting in the positive value rather than making the y coordinate be positive. So 3, 7's gone off, 2, 5, 1, 3, 0, 1, minus 1, 3, minus 2, 5. So that's gone down there. And then up to there. So this one, as you can see, is a mirror image in the y-axis. This bit, the whole thing is the modulus graph, but this stick here, this is y equals 2 positive x plus 1. This one is y equals 2 times negative x plus 1. So if you think of the two separate bits, you've got one bit where you've got the positive version and one bit where you've got the negative version. Okay, so it's ever so slightly different. If it was the modulus of the whole thing, it would come down here and then bounce back up. So this one, this is the bit of the graph, the bit of the normal line that exists. If I was to carry that on, like that, this is the only bit of the normal line that exists. So for where x is positive, the graph exists. Where x is negative, it's a reflection of what's in that right-hand side of that y-axis. Let's have a look at a quadratic. So x squared minus 2x, modulus x squared minus modulus 2x. When x is 3, modulus of 3 squared is 9, minus 2 times modulus of 3. That's 6. 2 squared minus 4 is 0. 1 squared minus 2 is minus 1. 0 minus 0 is 0. Minus 1 modulus is 1 squared minus 2 times the modulus of minus 1. So basically we're doing positive 1 squared minus 2 times positive 1. And then where x is minus 2, we're actually doing positive 2 squared minus 2 times positive 2. Okay, so we've got 3, 3, 2, 0, 1, minus 1, 0, 0, minus 1, minus 1, and minus 2, 0, and the other one would be there. Okay, so we end up with this bit okay, so x squared minus 2x would look like that, but then it would carry on. That's x squared minus 2x, okay, where x is positive. So for positive x coordinates, we have part of the graph, the proper graph. Where x is negative, then we've ended up with a reflection of what we've got on that right hand side of the y-axis. So we've got a W shape. So this bit is part of what would be considered the original graph of y equals x squared minus 2x, where x is greater than 0. So here x is all that side is where x is greater than or equal to 0. This is then the reflection of everything on the right hand side of that y-axis. Okay, so you've got two types. One type where the graph is normal apart from when it goes below the x-axis it gets reflected. And then you've got the other type where x is positive the graph exists, where x is negative it's a reflection in the y-axis. Okay, so just to summarise, to sketch graphs of the form modulus f of x, sketch the normal graph and then reflect any parts where the y coordinates are less than 0 in the x-axis, and then delete the bits that you don't want. To sketch graphs of the form f mod x, sketch the graph of y equals f of x for x is greater than or equal to 0 and then reflect that in the y-axis. Okay, so I'll just show you with a few examples of some sketches. So let's say we want to sketch y equals modulus of 2x plus 5. Okay, so 2x plus 5. So what you could do is with your pencil just draw a faint graph. So y equals 2x plus 5 is going to cross the y-axis at 5 and have a gradient of 2. So it might look something like that. Okay, so it says sketch the graph, reflect any part where f of x or y is less than 0 in the x-axis. So at this point here, this bit here, from this point here, has to be reflected in the x-axis. So that's going to come up like that. And then you can delete. So if you're doing it, you can just rub it out then. So I would, with a faint line, draw the actual line in, then reflect, and then rub out the bit below the x-axis. So remember, these ones, you shouldn't have any marks below the x-axis. Okay, so get rid of that one. So let's have a look at another one. Let's say we've got y equals, let's have a cubic, x minus 1, x plus 2, x plus 3, modulus. So we've got a cubic, that's going to go through 1 and minus 2 and minus 3. And go through minus 6 on the y-axis. Okay, so in terms of the actual graph, that's going to go up like that, down through there, and then back up like that. Okay, So this bit and this bit are above the x-axis. The rest of it needs to reflect. So this bit is going to come up and reflect like that, and then this bit is going to come up and reflect like that. That'll go through 6, and then that bit then needs to get rid of. So it'll look like that. So they can look a bit odd. Just do another one. Let's do y equals e to the mod x minus 3. This will be a nice one. Okay, so y equals e to the modulus x minus 3. So let's think about what e to the x minus 3 looks like first. Well, there'll be an asymptote at 3. And then instead of going e to the x goes through 1, so e to the x minus 3 will go through minus 2. So if we draw that graph in, that is going to look like that. Okay, now this one is that second form. To sketch graphs of the form f mod x, sketch the graph of y equals f of x for x is greater than or equal to 0, and then reflect this in the y-axis. So where x is greater than or equal to 0 is just this bit here. So this bit actually needs to get reflected in the y-axis. And then that bit doesn't exist. So that one would look like that. Okay. Let's do one more. Y equals, let's do a trig one. Let's do cos mod x for minus 180 to 180. Okay, so let's think about what cos looks like from minus 180 to 180. Oh, no, that's a bad one. Why is it a bad one? Because from minus 180 to 180, it looks like that. So it's already a reflection in the x-axis. That was a bad example. Let's do sine. Y equals sine mod x minus 180 to 180. So sine, normally from minus 180 to 180 would look like that. That's sine from minus 180 to 180. Sine of modulus x, everywhere where x is greater than or equal to 0 gets reflected in the y-axis. So that would actually look like that, and that bit wouldn't exist. Okay. Right, you've got all of these in your booklet. So there are 4, 8, 12, no, 4, 8, 11 to have a go at. Okay, so have a go at those, and we will look at the answers in the tutorial, or I will email them to you. Okay, but remember to do them in a faint, do the actual graph in a faint pencil, and then adapt them for the modulus. Then once you've done that, I'd like you to have a go at exercise 2E. And so it's just sketching modulus functions. And that's the end of this video for modulus functions intro.